Today's lesson is going to be on double displacement reactions. You will recognize a double displacement reaction because you're going to have a compound reacting with another compound. And be careful because we have seen a couple of reactions already, synthesis reactions in particular, where we already had two compounds reacting, but they were very specific. They were either a metal oxide with water or a non-metal oxide with water. So be aware that there are a couple of synthesis reactions that might fool you into thinking that they're double displacement. So you need to recognize those so that you don't get tricked. The general reaction for a double displacement, as we see, is any compound AB plus another compound CD. And I'll just comment, just like in single displacement reactions, these compounds have to be aqueous. Okay, so you have to dissolve those in water in order to get those ions freed up to interact and move around. And then we're going to switch partners. So we always say outside ions go together, okay, for a double displacement reaction. So I'm going to put AD together. And then inside ions go together. And notice how I direct those arrows. I start at the metal and I move over to the non-metal. So in the first pairing, A is our metal, combines with D. In our second pairing, C is our metal, and we're going to combine with the non-metal B. So just be aware that we flip those around a little bit. And the reason is we want to keep those metals as listed as the first element in the compound. Similar to single displacement reactions, double displacement reactions don't always occur. So they will only occur if a solid or a liquid or a gas is produced on the product side. And this is why states are so important that you have to be aware of them. If you form a solid on the product side, the only way you're going to know is you have to refer to a solubility chart. And that solubility chart will give you different combinations of ions that would be present in a compound. And it's going to tell you whether a precipitate will form or not. So remember that a precipitate is a solid, okay? And it will have the symbol S, and it'll be listed as an insoluble substance. It's something that does not dissolve in water. Gases will form usually from the breakdown of carbonic or sulfurous acid. And you may remember in our lesson on chemistry or chemical reactions basics, there are two reactions that show the decomposition of carbonic and sulfurous acid. So we have to be mindful of those and recognize when those two substances are produced that they will spontaneously decompose to form some gases. And the only liquid that will form is water. Okay, that is the only one that we will deal with in our course. And that is usually as a result of a neutralization reaction. So we did those last year in grade 10 science. This is when we take an acid and a base and we react them together. And water is one of our products. So just a side note on neutralization reactions, they are a special type of double displacement reaction in that we take an acid and a base, okay, so you should be able to recognize those, and then we produce a salt and water. Remember that a salt is not necessarily like table salt, sodium chloride. A salt is just the term used for an ionic compound, but specifically that compound is generated through a neutralization reaction. Okay, that's where the word comes from. So a reminder, we spent some time looking at acid nomenclature, but just a reminder that bases are going to contain either a hydroxide ion or a carbonate ion. Okay, so just a reminder about that as we go through and we see some of these reactions. So let's first look at a solubility chart and practice determining whether substances will form solids or not, okay? Or will these substances form a precipitate? If they form a precipitate, it means that they are not soluble in water. So you have a solubility chart that's been given to you. And what we do is you'll see all kinds of different ions listed there. And you look up the combinations of ions. Sometimes the ions aren't there. They'll just say most or they'll say all. But sometimes they're very specific as to which ions pair up and form either soluble substances or insoluble. And I just want to remind you that if it's soluble, okay, if it's soluble, we would state the state as aqueous. If it's not, this is when we would have a solid precipitate forming. So let's practice with calcium carbonate. So you will find calcium ion, but more likely you're going to find the carbonate ion. Usually they list them by anions first, and then match it up with a bunch of them. So if it says alkali ions, remember that alkali metals are in group 1. We're looking for calcium. So when you find the combination of calcium and carbonate, you're going to notice that it says low solubility. If it says low solubility, that means that this is a solid, and no, okay, it is not going to be soluble in water. Let's go down, so to silver chloride right here. So you'll find the chloride ion on your periodic table or on your activity series. And then look at all the different ions that it can pair up with and find silver. And if silver is not listed there, then again, you'll be able to know because it'll fall under all others or most. It just depends on the grouping. So you'll see that chloride with a silver ion is also not going to be soluble. So it's a no, which means that it's going to form a precipitate and it's going to use the state of solid. Let's go up to sodium bromide. So sodium bromide, you'll find the bromide ion. You'll find the sodium. It'll either be written there or it might say alkali ions because sodium is an alkali ion. It might fall under a category of all others. It all depends on the pairing. But you should notice that those two ions together are soluble. Okay, so you'll say, yes, they are soluble. And that means that you would be putting a state of AQ beside that formula. Lithium sulfide, find the sulfide ion. Lithium is an alkali ion. The pairing of those two together is yes. And again, that means that lithium sulfide would be aqueous and dissolve in solution. Let's look at magnesium sulfate. So magnesium sulfate, we can look at that pairing. And the sulfate ion with magnesium is soluble. And that makes sense because magnesium sulfate is what is in Epsom salts. And we know that those dissolve in the bathtub. So this would have a state of AQ. And then look up barium hydroxide. So you'll find the hydroxide ion, you'll find the barium ion either listed by itself or lumped in under all others. And when you see barium hydroxide, this does not dissolve. This is a no. And so we would give this the state of solid. Okay, let's practice writing out some double displacement reactions. So we're going to look at the first example that's here, sodium nitrate and magnesium chloride. So before we go to the trouble of writing out a full reaction, we want to make sure that it's going to take place. So remember that the only time that double displacement reactions occur is if you form a solid or a liquid or a gas on the product side. So let's just go through and look at the pairings here. So we know that sodium and chlorine are going to form one product. So why don't we go and look that up right now? So find sodium ion, find chloride ion on your solubility chart. And you're going to notice that both of those, so sodium and chloride, they dissolve in water. So they're going to be AQ. The other pair that we have will be magnesium and the nitrate ion. And when you look up those two, you'll find nitrate at the top of the solubility chart. And it'll say like pretty much anything that combines with a nitrate is soluble. So if we write out the formula for magnesium nitrate, then we know it will dissolve in water and it will also be AQ. So you see here that both of my products dissolve in water. I don't have a chemical change happening. I do not form a solid. I do not form a liquid. I do not form a gas. So this reaction does not occur. And so don't write those ions or those compounds. Write no reaction. If you write out those formulas, we assume that you think a reaction is occurring. Okay, so we don't want to do that. It's kind of nice when you notice that you don't form a solid, liquid, or gas because it's less work for you to do. Let's look at the next one. Hydrochloric acid and sodium hydroxide. So probably most of you, your radar should go up. You've got an acid and you've got sodium hydroxide, which is a base. Okay, so this is a neutralization reaction. We know this reaction is going to go to completion because neutralization reactions will produce water, which is a liquid. So we're going to start writing out the reactions. So we're going to take HCl, which will be AQ. We're going to take sodium hydroxide, which will also be AQ. They have to be to start that reaction. Those ions have to be freed up. Remember, outside ions go together. H and OH make water, which is a liquid. And inside ions go together. So Na and Cl get formed, and they are still going to be aqueous. If you didn't know that, you should know that. You should know salt dissolves in water. If you didn't know, just go to the solubility chart. And now you can look up the state of all these compounds in water. So do we need to balance? No, we don't. We have our liquid forming, so we know that this reaction goes to completion and we are good. Let's look at the next one. So we have barium chloride and silver nitrate. So again, before I write everything out, I would want to know, do I need to waste some time writing out formulas here? Let's go to the solubility chart and check out what's going to happen. So barium is going to rearrange and form with nitrate. All nitrates are soluble. Okay, so we know that he's going to be AQ. Then we're going to look backwards and say, okay, silver and chloride are going to form. Now we actually just saw that compound in the previous slide, but we go to the solubility chart and we notice those two form a precipitate. So let's write out the reaction because we need to put this to completion. We are forming a solid. So barium chloride is going to have the formula BaCl2. Okay, so don't forget, you got to look up the charge on each of them, crisscross rule, and this is going to be aqueous in solution. Silver nitrate, each have charges of 1, so you get AgNO3, and that is aqueous. We rearrange those ions, so outside ions go together. Barium and nitrate are going to form an aqueous substance based on the chart. And then silver and chloride, both charges of 1, form our precipitate, so it forms our solid. And then we need to balance. I need a 2 to balance those chlorines, and then I need a 2 to balance the nitrates and the silver. Okay, so let's look at our last one. Our last one is lithium carbonate and nitric acid. So here we are again. So we have an acid and we have a carbonate. And remember in our notes that we said bases are going to be hydroxides or carbonates. So we know that this reaction is going to occur. So I'm going to start to set this up right away because I know I've got a neutralization reaction happening. We're going to have a reaction go to completion here. So let's write out the formula for lithium carbonate. And again, you need to know nomenclature and your charges. Carbonate has a charge of 2, lithium has a charge of 1. Nitric acid is our oxy acid, so HNO3. This will be AQ. And then we're going to rearrange our ions and come up with our products. So outside ions go together. So we're going to take lithium with nitrate. And we know We just saw nitrate above. All nitrates are soluble. And then we're going to take hydrogen and carbonate and put that together. And when we do that, something should go off in your head. There it is. There's carbonic acid. And you know this is one of those compounds that spontaneously decomposes into water and CO2. So I'm actually going to erase some of this. And we know that the carbonic acid is actually going to form H2O, which is a liquid, and CO2, which is a gas. You have to know it, okay? You have to recognize it. And then we want to balance. So I'm going to put a 2 out front for lithium nitrate, a 2 in front of nitric acid, and then I believe everything else is balanced there. So there you go. Some, again, limitations on double displacement and incorporating the solubility chart, and also showing how important states are in balanced chemical reactions.